Ui.
Welcome to our ZEISS Innovation Talks, where we invite experts to discuss the latest innovations in industrial quality solutions. Today, we shine a spotlight on optical 3D solutions, and with me here is my colleague Carsten Reich, Head of Product Management and Application for Optical Solutions at ZEISS. Hi, Carsten.
Hi, Julia. Good to be here.
Great to have you here. Thanks for taking the time. Can you quickly introduce yourself and tell us a little bit more about your background and how long you are with ZEISS?
Since I did my master's research actually 30 years ago.
Oh, wow. Okay.
And then I had different roles, business development, sales, product development, and now product management.
Okay, great. Before we start and before we dive deeper into our topic of today, I want the audience to get to know you a little better. So I want to play a quick game with you. We call it lightning round. I give you two options. You pick one and then just quickly and spontaneous you answer the questions. Are you ready?
I'm ready.
Okay, so let's start. Mountain bike or race bike?
Mountain bike.
Combustion engine or e-motor?
Combustion engine.
Early bird or night owl?
There's something in between.
Okay, and inline or outline?
Both.
Okay.
Makes both sense.
That was good, thanks. Okay, so today we are talking about the power of digital twins, and we want to emphasize a little bit more about first the challenges of our customers and the trends in optical 3D, and then also what innovations we deliver for our customers to cope with these challenges.
Mhm.
And the title that you chose is quite interesting. It's quite fancy. What do you think about it? Is it a real trend or is it just a hype, in your opinion?
I would say digital twin is not a hype at all.
Okay.
It's an important tool. I would say a must-have tool for the industry today.
Okay, and why is this?
Yeah, because today the speed of innovation is very important for the
Everyone
industry.
talks about innovation.
Yes, speed of innovation is key. You want to be quick to the market. This means product cycles are shrinking,
Yeah.
complexity is growing, and there is less and less time for product development.
But I guess quality needs to stay at the same high level.
That's
very
a
high
challenge.
level.
That's a quality.
Okay.
Has to be as the customers are expecting this.
Okay, that's a real challenge. And how do you address these challenges?
By optical systems.
Okay,
This
so
is-
tell me more.
Yes, because if you want to be quick as a company, you have to change somehow. And today still there is too much product development with physical models.
What you mean, for example, the waterfall model where you just develop and
Yes,
okay.
step-by-step development, physical prototypes, optimizing in the physical way, building things, fixing things manually. And we think we can help you.
Yeah, there are other possibilities nowadays, right? By using software, digital tools.
Yes, digital processes are key here. So, and with the optical systems, we have the interface from the real world to the digital world.
Okay, that sounds easy, but I guess many companies struggle exactly with these challenges. So how do you approach this with your expertise and with your team?
Yeah, by using the optical systems, we can use the cameras, and each pixel of the cameras can be converted into a precise 3D coordinate. So
Okay.
instead of measuring objects by just a few points, we have a cloud of points. And this is then helping the complete process.
So what do you mean by cloud of points and how does it really appear then? I think you use software for that one. So can you tell me a little bit more? and
Yeah,
explain?
the typical approach would be first check the features of the parts. Are the holes at the correct positions? Are the bolts correctly, surface points, and so on? Are they all in tolerance? And we can extract the features out of the point cloud, the digital twin, to give this information, in and out information.
And how are these digital twins created? What are the methods to get them?
Yeah, I would say the most popular methods and technologies are laser scanning and fringe projection.
Okay, so laser scanning is with handheld systems? Okay.
Yes, we have the T-Scan Hawk 2, and you scan a part like you would paint with a brush a part, So you run around, go to every corner until you have the complete thing painted or in our case scanned.
Okay, and what about fringe projection?
Yeah, fringe projection, it's not handheld. It has to be stationary for the second that it needs to project different fringe patterns onto the object surface. But then you get a very detailed and accurate point cloud. And we can also adapt the field of view to small parts where you then get a very high degree of detail, but also with the ATOS LRX, for example, we have a system
parts.
with very large measuring volume up to 4 square meters, for example.
Okay, 4 square meter.
Yes.
Okay, that's quite large. So you don't need to distract parts, etc. You just leave them as they are and you walk around. But these are all manual systems.
These are
right?
manual systems. Yes.
Okay, and then you create this digital twin in a software. And then what are you doing with this?
The information that we have here, we can feed into digital processes.
What kind of digital processes?
I have one example here.
Okay.
And this process
what's that?
This is called, the digital process is called virtual clamping. And this is the back of an oven.
Ah, okay.
So, and this back of the oven, this is a wobbly sheet metal part. So, and if we want to measure it, we have to bring it into assembly position. Because later it will be assembled. And typically this is done by using physical clamping. So you have a fixture with clamping points and you clamp it at certain points and bring it at this certain point into the target position.
Okay, and then it's fixed in this position, which probably matches the cut file that you have in the software. And then you can scan it from all sides.
Yes, we scan it and inspect, for example, if all the holes are at the right position, if the surface is as expected and so on. But you can imagine that these clamping fixtures are not so easy to build because they have to be accurate. If they are not accurate, you're not measuring correctly.
Okay, so they have an influence on the data that you are creating.
Yes.
Okay.
That's the reason they cost a lot of money.
Yeah.
And for each part that you have, and we have customers that have more than 100 different parts, you need a different fixture.
And can we do it without the physical fixtures?
Exactly, yes.
Ah, okay.
We can use the virtual clamping here. And then we only need some support points. For this small part, we, for example, would need 3 support points.
Below the part?
Below the part. And then we can scan it. And of course, the part is now deformed by gravity and so on, but we can compensate it.
And
Once
you can later distract it in the software.
Yes, we subtract it in the software and then we apply with the forces the virtual clamping, bring it into the target position, and then we can do the inspection. And the only physical thing that we need are the supporting points.
Are these 3 points below? Okay,
yes, these
that's
3
quite
points.
Interesting.
We can also position the 3 points if you want to have it repeatably. We can use then the robot from the scan box, for example. Or if you have really serious inspection where you need to change the configuration quickly, this can be also done by robots, so fully automatic.
Wow, that's quite interesting. Thank you. So talking about full automation, you just mentioned it. So what are automation is actually everywhere. Everyone's talking about it. How can productions become more efficient, faster, and processes, of course, more automated? So what other solutions do you offer?
Yeah, automation is also key today for series inspection, also for optical metrology. And we have different solutions. So entry-level solutions where we have a small, some axes, for example, the scan port with the 3 axes, with only a rotation table, where you can put smaller parts. But we have also solutions like our scan boxes, where you can put small parts, but also large parts like complete car bodies inside. And
complete car bodies?
Yes, and then you do the full scan out of it.
Okay, that's quite interesting. So automotive is an important industry where optical 3D solutions are used.
Yes, but not only.
Okay, are there other industries?
Optical systems can be used everywhere.
What are other applications where this is relevant?
For example, machinery, medical,
Yeah,
aerospace.
metal parts.
Yes, a lot. For example, medical. You can imagine, for example, these implants or prostheses, they are all different, different sizes, different configurations and so on. And this is very good for the optical systems because we don't need to know exactly how the part looks like. We are looking from it from far away and then digitize it. And later then we can use the data. Okay,
understood. And getting back to digital processes that are based on the digital twin. We talked about virtual clamping. I also heard about or read about virtual assembly.
Yes.
What's that? Well, can you explain it a little bit?
Yes, here again, the benefit is avoiding doing things in the physical world. And for example, often parts have to be assembled. This is the
Manually, probably.
typical normal case.
Yeah.
For example, if you have a door and the car body, it has to be assembled later.
Sure.
And this takes a lot of time and effort to assemble it and then to measure if it's fitting correctly or not.
And if you then recognize that it's not fitting correctly, then you have to disassembly again and
Disassemble, do some optimizations, measure again if it's good or bad. And digital assembly means that you do the assembly process completely inside of in the digital world.
so in the software, so to say,
In the
based
software.
on the digital twin.
Yes. For example, Audi is using it this way. They're producing their doors for their cars in Puebla, Mexico, and then the car body in Ingolstadt in Germany. And then they scan the doors, send over the data to Germany, and they know in some minutes if these parts will fit later into the car body before the parts get onto the ship. And then they save a lot of time and can do a forecast of the final assembly.
So it's even an efficiency improvement across countries, really, and to make it more efficient to work across different production sites without recognizing.
Yes. And this saves a lot of time. For example, at our Berlin summit, Volkswagen was reporting this. They save 3 to 6 months using the digital assembly process.
3 to 6 months?
Yes, before start of production. That's a lot.
That's really a lot. Yeah. Okay. Wow. You mentioned Berlin, but I also recognized that lately in Stuttgart, you were launching a new system called Aramis One.
Yes.
Can you tell us a little bit more about what's the product about?
Yes, it's a testing product.
Okay.
So often our customers are also interested in the behavior of their products. How they behave under load, for example, or how they deform.
What are typical applications for this?
Yeah, for example, it could be what happens to windmill when you do an emergency stop. It's quite interesting. So,
wow, okay.
And then we can place some points onto it and then see how the tower moves when you do an emergency stop. It's a little bit scary, but this is an application. You want to know what happens, and these testing systems are used for this. Okay. Also for getting material properties. The Aramis One is very good at getting material properties. They do tests, like tensile tests, and then you know how a material deforms. And we use also this information for virtual clamping, because for the virtual clamping simulation, we need to know how a material behaves. Okay. And then you see we come back to the digital processes.
So it comes back to our back of the oven part that you just bring with us.
Exactly,
okay.
Yes.
Okay, that's quite interesting. I think we are getting closer to the end of our session, Carsten, but these are very nice insights and I learned a lot, and there's probably a lot more to learn for me. But if you could summarize this for our audience, what are your key takeaways of this session? Yeah,
it's all about speed, and we can really help here with our systems. The optical systems are the interface from the real world into the digital world. And so we can help here and feed the digital processes that lead to the speed that is needed today. Great.
Thank you very much, Carsten, for being here. Thanks for giving us the insights and talking about how we can really improve the go-to-market process, so to say, how to utilize the digital processes and tools better in optical measurement. And to our listeners, also, thanks for joining our ZEISS Innovation Talk about the power of digital twins. Stay curious, keep innovating, and see you next time. Thank you. Thanks, Carsten.
Thank you very much.